Today, we'll learn how to complete a statistical analysis of our amino acid sequences so that by the end of this lesson, you'll be able to create a statistical analysis similar to the internal assessment example accessed here and also below in the description. In order to do this, you will need your list of amino acid sequences. So this is my list of amino acid sequences, a new Google Sheets, and the amino acid statistics function, which is also linked below in the description. Now our tasks will be to find the number of essential amino acids in each amino acid sequence. Then we'll determine average, standard deviation, variance, and a new concept, coefficient of variance. We'll create a histogram to test if the amino acids have normal distribution, and then we'll create a table to perform a single factor ANOVA test using the Excel minor analysis tool pack, which you can download before we get started. Now there's an important note, and I'll be referring to this continually throughout this lesson. When we're comparing amino acid sequences for our statistical analysis, each amino acid is unique. So it's illogical to compare one amino acid to a different amino acid. For example, it's illogical to compare valine to leucine. But we can compare the number of valines in one amino acid sequence to the number of valines in another. Or, what we're doing, we can compare the number of valines in the amino acid sequence of a group of animals to another group of animals. This is a hard concept to understand, and I'll do my best with the metaphor. Say instead of amino acid sequences, you're comparing ingredients in a sandwich. You could say that each ingredient in a sandwich is unique, so it's illogical to compare one ingredient to a different ingredient in a sandwich. For example, it's illogical to compare the amount of turkey in a sandwich to the number of pickles in a sandwich. There's no relationship between the number of pickles and the amount of turkey in a sandwich. Each is unique to itself. One doesn't affect the other. But we can compare the amount of turkey in one sandwich to the amount of turkey in another sandwich. Like you can compare the amount of turkey in a Christmas sandwich to the amount of turkey in a Thanksgiving sandwich. Maybe a Thanksgiving sandwich has more turkey than another, but we wouldn't involve pickles or olives or lettuce because each of those are unique to itself in the same way that amino acids are unique to themselves. Or we can compare the amount of turkey in the sandwich of a group of Christmas sandwiches and in a group of Thanksgiving sandwiches. Maybe you get a bunch of different Christmas sandwiches and a bunch of different Thanksgiving sandwiches, and you can see and you can test that the amount of turkey in a Thanksgiving sandwich is much higher than the amount of turkey in a Christmas sandwich, and maybe it's because people have a lot of leftover turkey on Thanksgiving. But the key concept is that each ingredient in the sandwich is unique to itself, and so you would need to compare that ingredient in that sandwich to other sandwiches, but you wouldn't compare it to ingredients in the same sandwich. I hope that metaphor helps. It's the best I've been able to come up with since this is a higher concept, but hopefully if it doesn't make sense now, it'll make sense by the end of the lesson. So my group of Thanksgiving sandwiches and Christmas sandwiches, in this case, I decided to compare as groups of animals. So I looked at the amino acid sequence for different bats and for different primates. One way that you can search for these groups on NCBI is if we go to the homepage that we've been using a lot we'll type in our protein of interest. Remember, we're still on OR6A2, the protein O, protein cilantro. It influences whether or not you like the smell and taste of cilantro. We'll go to orthologs. And then it gives us a long list of organisms. Oh, it'll come any second. Like the house mouse, the human, the cattle, the dog. And in order to compare bats and primates, I just went to where it says search the taxonomy tree, and I clicked bats. And when you do that, it filters, so the only organisms you have are bats. And then if I wanted to do primates, I clicked primates, and it filters all of the organisms that are primates. So I'm comparing two groups, bats and primates. And I'm going to be comparing the amino acid sequence between these groups, specifically each amino acid, using a Wormley-ANOVA test. So I collected the first couple of amino acid sequences for each group, and I recorded them here. So we have bats and we have primates. And now we'll just go ahead and get started. So our first task is to find the number of essential amino acids in each amino acid sequence. You can start this by going to the amino acid statistics function and just copy the first 3 columns. Copy. And then go to your new spreadsheet and paste them here in A1. And then I created a function that copies over, and it will take and count the number of times that V appears in your amino acid sequence and record it here. So if we start with the first amino acid sequence, the greater horseshoe bat, I'll take the name, put greater horseshoe bat here, and then I'm going to take the amino acid sequence and copy that here. Now when you copy it here, if you just immediately paste it, it's going to take up a couple of rows and it'll look funky. You don't want to do this. You want to paste it into where it says FX at the top, because that'll prevent it from subsetting to different rows. So I'll paste it here. And now the function automatically takes the number of times V appears, L appears, I appears, F appears, W appears, etc. So I will do that for the rest of the organisms, but I'm only going to put the bats on this tab, and I created a new tab for primates, so I'm going to put the primates on a different tab just to keep it organized. I'll do this right now, but I'm going to zoom through it on this video. A quick point. In order to get the amino acid, number of amino acids for valine, leucine, etc., in the next column for the Jamaican fruit eating bat, you just copy these rows and you paste it in the next column. And again, since it's only copying the function, and the function will look at the column, the row immediately above it, then it takes the amino acid, the number of valines in this amino acid sequence. So we have 27 valines in the Jamaican fruit-eating bat. We have 28 in the greater horseshoe bat. We have 43 leucines in the greater horseshoe bat and 42 in the Jamaican fruit-eating bat. And then we would do this for the rest of our organisms. So since we are, the function that you would copy and paste is just the function, and it looks at the amino acid sequence above it and compares it to how many times this letter might appear in that amino acid sequence. You can, this makes it super easy. You can just copy whatever column has the rows with the function. So this, it's copied, and then if you highlight all of the columns, all of the rows for your target columns, and you paste it, it'll automatically fill in the number of times valine appears for this amino acid sequence, or for this one, etc. And this is how we're able to get the number of essential amino acids in each amino acid sequence. So now I'll also do this for the primates. And again, now that I have the organism, the amino acid sequence, I can just copy, this copies the function, and I'll paste the function into the other rows that I want. Oh. There we go. So now I have the number of essential amino acids in each amino acid sequence for the bats and for the primates. The next step is to find the average, standard deviation, variance, and coefficient of variance, so that you can create a table and make inferences similar to these ones. So you can apply what we learned from our statistical analysis review. And say in this column, I want to find the average, and then I'll find the standard deviation here, the variance, and the coefficient of, the coefficient of variance. My keyboard is short-circuiting. So you can just type in average, and it automatically suggests the row. So take the row. And then it says autofill, so you can automatically fill the rest. Yes, I'd like it to automatically fill the rest. So now this is the average for valine, for leucine, for isoleucine, phenylalanine, etc. Now, these numbers are a little bit long, and something you can do to make them shorter is to round to significant figures. The function that you would use for this is called round, and say that I have this, so instead of using just the average function, I would do equals round, and then it asks for the value followed by the number of places we want it to round by. So the value I want is the average of this row, and the number of places I want it to round by is, let's say, 4. And that also gives you the average, but it makes it look a lot nicer. because it automatically rounds it. We can do this with standard deviation. And then it suggests autofill. If this doesn't suggest it for you, you could also copy the first standard deviation you did and paste it, the function. The function will automatically look at the next rows, and it'll give you the standard deviation for each row. But again, I want to round it. And instead of typing round into the cell, you could also type it up here where it says fx, and I want to round it by 4. So that gives a nicer number, a nicer looking number. And I'll do that for the rest. Now variance. And then I'll take it and I'll copy the variance into the remaining. And again, this would be good to round. Now, there we go. The coefficient of variance is just the standard deviation divided by the mean. So you just take the standard deviation here and then divide it by the mean, or the average. And if this gives you relative variance, which is a better indicator when you're dealing with things that are more unique to themselves, like we were talking about before. And so if the coefficient of variance is ever greater than 1, that signifies a really high amount of variance, and if it's less than 1, then a lower amount of variance. So I'm going to add round to this as well, 4 decimal places, and I'll paste that for the rest of the columns. So the coefficient of variance is low for all of these, so it indicates low variance, low relative variance. And then I'm also going to do this for the primates, but I will zoom through it. So now we've done this for our bats, our first group, and we've done it for the primates, the second group. And then you can paste it into your internal assessment, make it look a little bit nicer, maybe add some colors, remove the amino acid sequences, only include the name. Make sure that when you paste it, you only paste the values, or else it'll just copy the functions over and it won't return anything. So we learned about pasting values in the statistical review. The next step is to create a histogram to test if the amino acids have normal distribution. This is going to lead us to whether or not we can use a statistical test that uses normal distribution, like the t-test. And if it doesn't have normal distribution, then we can't use the t-test, and we'd have to use something else that doesn't require normal distribution. As a reminder, normal distribution is just if you plot it on a histogram and it looks like the shape of a bell, then it has some normal distribution. I'll show you what this looks like, normal distribution bell curve. So if when you plot it, it looks like this, has this shape of a bell, then it has normal distribution, and we can use something like the t-test, which requires normal distribution. So let's just take a random sample. Remember, since we're going to be performing the statistical test on the amino acids, not between, like valine and leucine, but rather on valine and compare it to another group, then let's just start with just a histogram of the number of valines in primates. So we would highlight the data that we want, go to Insert Chart, and it'll automatically suggest something. Sometimes it's a histogram, and sometimes you need to change it. So this is not a histogram, it's a column chart. So we'll go to Setup, Chart Type, and go down to Histogram at the bottom. Now, in order to change what's called the buckets, or the amount of like what's included for each column, for example, it's showing that 2 sequences are between 25 and 28, but to make it so that each individual number is represented on this histogram, we can go to Customize, Histogram, Bucket Size, and we can change the number of buckets. So if we go to 1, it'll split it up so that it'll show the number like of amino acid sequences that have 27 valines or 31 valines, and it'll divide the x-axis by increments of 1. We can make it 2 or 5. If your histogram looks weird, I would recommend playing with the bucket size and seeing if it changes anything. Of course, we'll add labels. So this is the number distribution of valines in the amino acid sequences of primates. Counts. And then we have to add the x-axis. Number of valines. So as you can see, this does not represent a bell curve. It doesn't start by going up and then going back down. What we would call it's skewed. So, and if you sample other amino acids like leucine, isoleucine, you'll see the same thing. We don't see bell curves. It's going to be important to include it, other ones in your internal assessment to illustrate that you know and you've taken the sample. But the purpose of this is just to illustrate how to create the histogram so that you'd be able to do it when you're working on your internal assessment. So we've created a histogram to test if the amino acids have normal distribution. Now, the next step in our analysis is going to be create a table to perform a single factor ANOVA test using the Excel minor analysis tool pack. This is more intensive. We're using a single factor ANOVA test because it doesn't require normal distribution, and we've seen that our amino acids don't have normal distribution, so we can use this. We would use a t-test if this was shaped like a bell curve, but we can't. And that's another really interesting connection, is a single factor ANOVA is like a t-test, but it's for things that don't have a normal distribution. So this is for the primates, and I'm going to take the row of valines, and I've created a different sheet called bats versus primates. And if you just paste it directly, since it pastes the function, it's not going to copy what was on the previous sheet. You need to do paste special, paste values only. So this is for the primates. And then you want to take the number of valines for the bats. Bats. Again, you need to do paste values only. So these are the number of valines in different amino acid sequences for the primates and then for the bats. once you've downloaded the tool pack, you'll go to Add-on, Excel Minor Analysis Tool Pack, Start. Then you'll click on Single Factor ANOVA, which shows up at the top. It asks for an input range. We've decided our probability value is 0.05, so if it's below 0.05, it's significant. If it's above, it's not. And then the output range is going to be where it displays the results. It is a little bit finicky. I'd recommend testing it. For the input range, you're going to input and highlight the values between the groups. And then it asks, is it grouped by columns or rows? We're grouped, primates are in the second row, bats are in the third row, so it's grouped by rows. And then after you've highlighted this, when you click on the input range, it'll automatically fill what you have. For the output range, you could click any cell. And again, it'll automatically fill where you've clicked. Then you can click OK, and it'll calculate the single factor ANOVA. It'll give you a table that looks like this. The only value that you would need to pay attention to is where it says p-value here. And we can record the p-value. So the p-value for between valines in primates and valines in bats is going to be 0.049, which is 4.9%, which is statistically significant because it's lower than that 0.05. So there's a statistically significant difference between the number of valines in primates compared to bats. It gets tedious because you need to do this for every amino acid. So primates, bats, starting with primates. The next one is leucine. And then for bats, right, so you have to paste special paste values only. And then we will calculate our ANOVA again. So we have our input range this time is going to be the next two rows. Primates are on row 4, bats are on row 5, so they're grouped by rows because one group is primates and one group is bat. The output range is you can just click any cell as long as you have space. And then we'll click OK. And now it returns a p-value of 0.016, which is also statistically significant. It's less than that 0.05. So there's a statistical significance between the number of leucines between primates and bats. And then you'll just keep doing that for the rest of the essential amino acids. And then you could put that into a table. That's what I did for the internal assessment, where I just grouped each row together and then performed the one factor ANOVA test. And then I just took this. See, what I'm doing here is just what I did over here with the p-value. And I just took this, and that's what you see and I put down, this is associated with valine, this is associated with leucine, and that's what you can see in our statistical analysis section, how there's a statistically significant difference in the number of valine amino acids between each group. So that is our last task. So, thanks for watching. By the end of this lesson, you should know how to complete a statistical analysis of your amino acid sequences that you can use for the internal assessment. We found the number of essential amino acids in each amino acid sequence. We determined average, standard deviation, variance, and coefficient of variance. Then we created a histogram to test if the amino acids have normal distribution, that bell curve. And finally, we created a table to perform a single factor ANOVA test using the XL Minor analysis toolpack. Let me know if you have any questions, and good luck.